Gravitation. See, this is lecture 1 and we will go into few observations. Gravitational force is a fundamental force amongst the 4 fundamental forces we have. What are the 4 fundamental forces? Number 1 is, gravitational force. Number 2 is electrostatics or electromagnetic forces. Number 3 is the strong force. Number 4 is the weak force. These two are short range forces. Basically nuclear forces, they act within the nucleus. So we are not concentrating on these two forces, we are concentrating mainly on this. I have written this because there are few similarities between this gravitational force and this electromagnetic force. We shall discuss this. But let's start with gravitation first. So what are the observations which we made in gravity? First, as far as Aryabhatta is concerned, he observed that Earth is rotating about its own axis. It's 5th century AD. Then he also observed few celestial bodies. The motion of celestial bodies are observed from the surface of the Earth. Then Kepler came into play. Kepler's 3 laws. All these laws are related to planets, big things. Why? Because as far as gravitational force is concerned, this force is basically very weak. Weak means, what shall I say, you need very big masses to get the manifestation of this force. On the contrary, as far as this, if you take tiny protons, right? If you take tiny protons, then those two protons will repel, or a proton and an electron will have a force very high, right? But a proton and two protons will have a gravitational force which is very low. In fact, the order, if you can measure, suppose this is a nucleus, and suppose here is a proton and here is a proton, the order of repulsion, so that's an electrostatic force divided by order of gravitational force, means the attraction. I am talking only of the magnitude. It's approximately 10 to the power of 36. So imagine how huge this electrostatic forces are. So gravity is very weak force, but very, very fundamental forces, very fundamental. And this is a long range force. Even if you have a mass at infinity, you have a mass here, they will attract. There are a few differences between gravitational force and electrostatic force. Let me point, as I am mentioning gravitational force and electrostatic forces as observations are concerned. Let me not go into the mathematical details. You suppose you have a mobile phone and you do not want to speak with your friend. Suppose there is some tiff and you don't want to speak with your friend for some time, and you also don't want to miss him or miss her, because you don't want to lose the friendship. So temporarily what you want is, you want to send a message that you are unreachable. So what do? You take this mobile phone, suppose this is the mobile phone, place it in a metal container. So this is metal, and just ground this container. Just ground it, place it somewhere so that it is well grounded, well earthed. Electromagnetic waves will not enter. It can be shielded. You can shield an electromagnetic force. This is one of the fundamental difference. On the contrary, suppose you have the surface of the earth and you have a building, 1 store, 2 store, 3 store, and if you want that, you don't want yourself to be pulled by the earth and you go and stand here, so you want a surface which can shield or you want to put yourself in a box and want the gravity to not get into you. It's not possible. So gravitational force cannot be shielded. It can be shielded only if you go in favor. So I'll come to that also. Suppose if you are in a box and if you are thrown from the space, you are coming down, you will feel weightless. The only way you can shield gravitation if you go in favor to it. So, but as far as electromagnetic forces are concerned, you can shield, right? So point number one, first difference is main important electromagnetic fields can be shielded, but gravitational fields cannot be. This is one important difference, right? Difference I am talking. Point number two, this you all know, electrostatic forces are both attractive as well as repulsive, but gravitational forces are always attractive. And they are definitely gravitational forces are weak. So this is the third point. You observe that the forces between two protons in a nucleus, the electrostatic force of repulsion between two protons is of the order of 10 to the power 36 times the force of attraction between those two protons by gravitation. And there are similarities, you definitely know, because these two forces are also inversely proportional to the square of the distance. As you go apart, the forces fall by square of the distance, and also gravitational force is proportional to the square of the masses, but electrostatic forces are proportional to the square of the charges. Anyway, we will not go into electromagnetism, but this is just an introduction, so I just mentioned few points, that's all. Let's concentrate on gravitation first. So the important thing is you can't shield gravitation. This is very important. You cannot shield gravitation. So how can you manage? How can you manage gravitation? You can manage gravitation only if you go in favor to it. So if you can manage gravitation if you only go in favor to it. So you can remove or feel weightless if you move in favor to gravitational fields. Okay. Now let's directly come to Newton's gravity. I'll not go into any Einsteinian gravity, because that is a completely different thing, different approach. It is matter and energy replaced by geometry. That's not in this course in your plus 2 level. But as far as Newton's gravity is concerned, let me mention few things. There's a problem with Newtonian gravity. What is the first problem? Suppose you have a mass here, let me m1, suppose you have a mass m2, and let me put the law first. So the force of attraction is proportional to the square of the product of the masses, inversely proportional to the square of the distance between them, and the constant of proportionality is g. And it's along the direction of this radius vector joining these two, and this is attractive. This is attractive. Let me tell you one thing. These this law is the problem. There's some problem with this law. The problem is, suppose you have a change in the mass here. If suppose some mass came in, suppose there is some additional mass, this m1 changed a little bit, you will not get the effect in m2 immediately. But here is no message like this. There is it says that it will be immediately affected, right? See, I see another person only after the light signal comes from that person to me. Also, as far as gravity is concerned, any changes in a mass will be affected only after the gravitational field reaches that another mass, and that moves same with the speed of light. So you will this law is basically, it's true, it's very true, but there are some deficiency in this law. This deficiency which I mentioned, this is very important. Okay, and as far as this masses are concerned, to get a manifestation of this law, this mass should be very big. We only talk of celestial bodies, Earth, Sun, planets, and everything, right? So you have to think of big masses. You have to think of big masses and big things to get a manifestation of gravity. Another important thing is you have to think in a different way as far as you are studying physics. See, an apple fell from a tree. We usually have a habit of standing on the surface of the earth. See, the apple is falling. Newton also saw an apple falling from a tree. But the thing is, his attitude towards looking to the situation is different. He saw something is coming to the earth. It's not falling on the surface of the earth, rather it's coming to the earth. He actually went into some different space where the earth and this tree is, everything is embedded, and he is seeing the system from outside, and he is seeing that the apple is coming to the earth, and immediately he took it, he tried to write the law of nature, this law of nature. See, what is physics? Physics is basically, if you say that how nature works, and if you ask physics why nature works, why the apple is falling from a tree, it is no physics. You have to give a mathematical law behind it, right? Why apple is falling from a tree, that is due to gravitation, that's all. That is no physics. You have to give a mathematical law that the force is proportional to the product of the masses, inversely proportional to the square of the distance between them. And you have to bring this by few observations, taking few measurements, and Newton also got this G as 6.67 into 10 to the power minus 11 SI units. Okay, you can easily write, if this is Newton, this is length square, this is kg, so the unit is Newton. Meter square kg minus 2. You can also break it Newton is kg meter second square. This is meter square, kg minus 2. So first, if you take it mass m cube time minus 2 kg inverse. So that's the unit of the gravitational constant g. It's a universal constant. It's a universal constant. Three universal constants are there. One is g, which is basically which connects celestial bodies. There is also another universal constant which we know, that's c. It's 3 into 10 to the power 8 meters per second. It's approximately something 2.99 something. It's approximately 3 into 10 to the power 8 meters per second. That's the gravitation. That's the velocity of light. Basically, this is the upper limit for physics. We are only able to measure only after the signal comes with this speed to our eye or to our observer, right? So that's the upper limit, and also there is a lower limit, h cut or h. That's the Planck's constant, something 10 to the power minus 34 joule second, something 10 to the power minus 34 joule seconds. Okay, so this is the lower limit, this is the upper limit, and this is the connection. I tell you, you can express everything in terms of these three constants. The fundamental units are mass, length and time. You can replace mass, length and time by g, c and h. Okay, that's we are not going to do here. This is more or less an introduction. I have to go into the laws. Let me start with Kepler's law because it came before Newton. So then we will deduce Kepler's law after we go into gravitation. So let me start with Newton's gravitation first straightway, because that is which is important, and that is in our course. So let's start with Newton's law of gravitation. So Newton's law of gravitation. Now F, force, is G m1 m2 by r square. Let me speak of the magnitude only first. So now this m1 and m2, what are these? These are masses. Not exactly masses, I tell you. These are gravitational masses. There are mainly two kinds of mass. Another is the inertial mass. For example, suppose you have a mass m. You are giving a force, and this fellow, force F, suppose this is F1, and this moves with an acceleration a. So F1 is mass times acceleration. And what is this mass? This has nothing to do with gravity. Here there is no gravity. In free space, where there is the gravity is very, very, very weak, or there is no gravity, everything is suppose balanced. This force is basically mass times acceleration, and this mass is an inertial mass. Suppose you are moving in a bus, the bus decelerates, you jump, you move forward. The bus accelerates, you move, you go back. Even if you sleep in a bus, or you close your eye, you will feel whether the bus is turning right, turning left. Just how you come into a non-inertial frame of reference, or you come into an accelerated frame of reference, and your inertial mass generates a you come into a non-inertial frame of reference and you feel a force which is called the pseudo force, depending upon the direction of the motion of the bus. And in this case there is no gravity involved. So this is basically the inertial mass. I give you an example. Suppose if you are in a lift, and suppose you are in a box, what I was telling at the start of this lecture, and you are thrown from space. It's coming with an acceleration g. What happened? This you will immediately come to a non-inertial frame of reference and you will feel an acceleration g upward. Now you have a gravitational mass mg times g. You are being pulled down, and you also have a inertial mass which is exactly same. Many times this pseudo acceleration which is acting up, and this two gets cancelled and you will feel weightless. Okay. Many scientists tried to prove that these two are different, but they could not. And this mg times g equals to mi times g. This is called the principle of equivalence. This is a law of nature. This is a start of general relativity, the Einsteinian relativity, where actually we equate matter with matter and energy with geometry. We'll not go into that here, definitely. But let me tell you that whenever you write these force laws, keep in mind that this mass is an inertial mass. This is not a gravitational mass. This has nothing to do with gravity. Gravitational mass only plays when there is a gravitational force acting on it. Suppose I am standing, I am being pulled by the earth, I have a mass, this is my gravitational mass is being pulled by the earth, and my force I'm giving a mg on the surface, right, where I'm standing. So keep in mind, whenever you are moving, keep this in mind, whenever you are moving, you experience a force. Suppose if you are accelerating, you experience a force backwards. If you are decelerating, you experience a force forward. All these forces are due to your inertial mass, not your gravitational mass. Gravitational mass only takes place when the gravity is involved. In fact, this gravitational mass are classified into two types of mass, two types of gravitational masses that you need to know now, but anyway I'm telling. One is the active gravitational mass actually, and another is the passive gravitational mass. Active gravitational mass is the mass which creates a field, and the passive gravitational mass is basically the test mass. It also creates a field, but we consider the test masses as if they do not create a field. They are being put into the field of some other active gravitational mass bodies, and we test the force and we find the field of that active gravitational mass bodies. Anyway, that is not important. Try to have a distinction between two masses. One is the gravitational mass and the other is the inertial mass. From the next lecture, I shall go into mathematics, and will deduce a few expression and all, and I shall do it in the shared screen way in my software. But I am doing this first lecture in this board just to explain how things work. Go and read the book. H.C. Verma I prefer. You read the H.C. Verma, and whenever you feel like doing something more, a little, you want to go ahead, if you want to ask, you can go to my channel, and if you can have comments, I'll definitely answer any reference books, notes, anything you want. You can have subscribed to my channel. Notes will be given in the description box. Thank you very much.